Good morning, friends. I'm Sunita Fadkule, Professor in Mechanical Engineering at JSPM's Jaywantrao Sawan College of Engineering, Hadapsar, Pune. This is our video lecture number 32, which is on unit number 4, that is balancing. Today we are going to start reciprocating unbalance, in which we are going to study single cylinder engine, balancing of single cylinder engine. Learning outcome is you will be able to analyze the unbalance of single cylinder engine. So what we have learned in earlier lecture about the two conditions for rotary unbalance. The first condition is summation of forces is equal to 0. That means you must get closed force polygon. And second condition is summation of couples is equal to 0. That means you must get closed couple polygon if your system is completely balanced. Now today we are going to start new topic, okay, that is balancing of reciprocating masses. Okay, so why reciprocating engine balancing is important? Okay, it has been always concerned about the engine. You know how engines are used. So any unbalance within an engine, it results in fatigue and failure. Also excessive vibrations will be there and noise will be there, which may be of airborne type or structural noise. So to avoid this one, we have to balance the engine. Okay, so a typical slider crank mechanism is used in IC engine, which is shown in the diagram. See, this is the typical slider crank mechanism. So this is the piston, connecting rod, crank, and this is the crankshaft. Okay, then you will see the notation. R is the radius of the crank, L is the length of the connecting rod, theta is the angle made by the crank with the line of stroke, phi is the angle made by the connecting rod. Okay, so this is a typical slider crank mechanism. So it consists of these four parts, and crank is undergoing purely rotary mechanism, rotary motion. It will have a rotary motion purely, and piston will be having pure sliding motion mechanism, sliding motion. And what is the motion of connecting rod? Because connecting rod will connect piston and crank. So at one end it is rotating completely, at other end it is sliding completely. So what is the type of motion connecting rod is having? It is a oscillatory type motion. Okay, so because of this one, inertia forces are developed. Okay, inertia forces, those are given. How to find out those inertia force? We know Newton's second law of motion, which gives us accelerating force F is equal to ma. Okay, so that creates the unbalanced force, and that is nothing but the inertia force. Okay, so inertia force, it is also known as a shaking force or shaking moments due to the moving parts of the frame, that is a cylinder block. Okay, so we have studied in theory of machine 1 that how to find out acceleration of the piston analytically. Okay, this is the formula which we have derived, we have studied in theory of machine 1. So acceleration of the piston, that is AP, is equal to r omega square cos theta plus cos 2 theta by n. Okay, so this is the acceleration of the moving parts. How to find out force then? Force is equal to mass into acceleration. Okay, mass of the reciprocating parts. So m into r omega square into bracket cos theta plus cos 2 theta upon n. So if we split this or open this bracket, we will get two terms. F is equal to mr omega square cos theta plus mr omega square cos 2 theta upon n. Okay, so out of these two terms, the first term, that is mr omega square cos theta, is called as a primary force. Okay, so primary inertia force or primary accelerating force. And second term, that is mr omega square cos 2 theta upon n, it is known as a secondary accelerating force or secondary unbalanced force. Okay, so these are the two forces we are going to study in detail. So if you consider now what we have learned in rotating unbalance and what we are studying in reciprocating unbalance, in rotary unbalance, there were only two polygons we had studied. Okay, that is force polygon and couple polygon. Here also those polygon we have to draw only, but new two terms have been added here. What are those two terms? Primary unbalanced force and secondary unbalanced force. Okay, So this is the magnitude of primary force, secondary force. What is the maximum of primary force when cos theta is 1? So that is maximum value of primary force is mr omega square. What is the maximum value of secondary force when cos 2 theta is equal to 1? So it will be mr omega square upon n. Now if you compare these two values, okay, which will be smaller? Naturally secondary force, because this is divided by n. What is n? It is the obliquity ratio. That is, it is the ratio of length of connecting rod to the length of crank. That is L upon R. And it is usually falling between 3 to 4. So primary force magnitude is larger, almost 3 to 4 times than secondary force. So if engine is running with very slow speed, you need not balance for secondary forces because already its magnitude is very small. But for every engine, it is necessary to balance the primary force. Once you balance the primary force, even if it is high speed engine, then you go for secondary force, secondary balancing force. Okay. So now there are two types of balancing of the engines we are going to study. First is balancing of single cylinder engine. Once we know this theory, then we can go for balancing of multi-cylinder inline engine and multi-cylinder radial engine. So today we are going to study balancing of single cylinder engine. Okay. The inertia force due to primary accelerating force, we know it is given by figure A and B. Okay, we'll see that figure. And the forces acting on the engine frame due to these inertia forces are shown here. Okay, see here. This is the diagram. This is the forces shown acting on the slider crank mechanism. So basically, this is the crank rotating in anti-clockwise direction. So this crank will exert the force on the crankshaft in this direction, and the reaction will be in this direction. Okay, you know, unbalanced force means inertia force, which is nothing but the reactive force in the opposite direction. So this crank is rotating in anti-clockwise direction. So crank exert the force on this crankshaft in this direction, in perpendicular direction. So what will be the unbalanced force? In the opposite direction, that means in this direction. So this is shown here. So this is F21. 2 is the crank, 1 is the fixed link, that is crankshaft. So bearing, you can say. So what is the force acting on the bearing here? Crankshaft bearing F21. Okay, 2 by 1. Now if you resolve this force into two components, this is a horizontal component FH21 and this is the vertical component FV21, vertical and horizontal. Okay, then here there is a cylinder. So there is a reactive force, reactions offered by the cylinder on this piston, that is F41. Okay, because it is sliding, so force will be perpendicular. Okay, now see this F21 force vertically downward. Okay, this is vertically downward and this force is vertically upward. Okay, so these two forces will form a couple in anti-clockwise direction, and this couple will try to shake the engine to jump, or to, you can say, to unbalance the engine. Okay, so these two forces will form a shaking couple. Okay, so that your engine can jump, okay, and or vibrate, you can say, basically. And this force is remaining FH21. This will remain as it is, and this is the unbalanced force. See the direction, and the direction is very important. See here, it is shown. Here it is shown by only primary force is shown here, mr omega square cos theta. How this direction is there? See, if crank is rotating in the anti-clockwise direction, it is moving in that direction. Unbalanced force will be in the opposite direction, so that means towards right. Okay, so this is nothing but this force has been shown here. This is your unbalanced force FH21. Okay, it is shown here mr omega square cos theta, inertia force or unbalanced force. Okay, so let us see here what we have written. The force exerted by the crankshaft on the main bearings has two components, FH21, FV21. The horizontal force FH21 is an unbalanced shaking force. Okay, as I told you, that is nothing but the unbalanced force or inertia force. The vertical forces FV21 and FV41 balance each other, but for an unbalanced shaking couple, the magnitude and direction of this unbalanced force and couple go on changing with the rotation of crank angle theta, because theta changes from 0 to 360. So the magnitude of these couples and force and direction, that is also changing as theta changes, because theta term is there, na, cos theta, cos 2 theta. The shaking force produces linear vibrations of the frame in the horizontal direction, whereas the shaking couple produces oscillating vibrations. Okay, so this engine will oscillate like this because of the shaking moment. Okay, and this is the unbalanced force, so this will create the vibration like this along the line of stroke, along the horizontal direction. Okay, so we have to balance this force. Okay, so naturally this force should be as small as possible, which will have the two component. So let us see here. So this is the shaking couple which produce. Now it is seen that shaking force FH21 is the only unbalanced force. Okay, it may hamper the smooth running of the engine, and thus the effort is made to balance the same. Okay, however, it is not at all possible to balance it completely, and only some modifications can be made. That means what? This force is unbalanced, no? This FH21. So how this has balance, that we are going to study, but that will also tell us that we cannot completely balance it. Some part of unbalance will always remain there. Why? Let us see here. Now see, the usual approach of balancing the shaking force is by addition of a rotating counter mass at radius r, directly opposite to the crank, which however produces a partial balance. That means what? See, this is your crank. Now how to balance this? Okay, how to balance this unbalanced force? See, what is the unbalanced force? This one. What is the magnitude? Mr omega square cos theta. As this crank is rotating in this direction, at this moment balancing force direction is this one, Mr omega square cos theta. Now you have to balance this force. Means what? Now assume that here it is a reciprocating mass which are here, those are assumed to be placed here, assumed to be imagine here placed. So how do you know how to balance the rotating, as if now this becomes the rotating unbalance? Now you know how to balance this rotating mass, just in a single plane only, in the same plane you provide the other mass. Okay, so mr must be equal to mbrb. You know, this is the procedure. Okay, so here also we are going to adopt the same procedure to balance the rotating unbalance. So the opposite to the crank, which however produces a partial balance. Now this counter mass is in addition to the mass used to balance the rotating unbalance due to mass at the crank pin. Okay, so that means how much already there is a unbalanced mass due to crank pin due to here. So in addition to that one, because of this component of the force, okay, more unbalance will be created. And how much is that unbalance? Mr omega square cos theta. This we have to balance now. So for that purpose, we are providing a mass at a certain radius, that is at a radius r only here. So what force it will produce? Mr omega square in this direction. You know, this is the centrifugal force. So now this Mr omega square has two components. One is vertical, other is horizontal. Now as this angle is theta, this is opposite angle, it is also theta. So what are the component of this Mr omega square, which we have provided the additional mass opposite to the crank? So what are its two component? This component is cos theta. Okay, Mr omega square cos theta. This component is vertical component, which is Mr omega square sin theta. Now see, this is basically our unbalanced force, Mr omega square cos theta. Primary force. We are talking today only about the right now, about the primary force. Later on, same procedure has to be followed for secondary force. So what is the primary unbalanced force? Mr omega square cos theta. Now see, the component of this force, Mr omega square cos theta, will be neutralizing this force. So this is opposite to this force. So that means what? Mr omega square cos theta, we have balance. Correct? But what has happened? See, new component has been created, Mr omega square sin theta, in the vertical direction, that is perpendicular to the line of stroke. So now this component unbalance will remain here, no? How can you remove this? So that means even if we try to balance the engine, single cylinder engine, by providing certain mass, by taking the care that MR must be equal to MBRB. Okay, but it will not completely balance the engine because this component will be remaining over there. So means what we did, we have balanced this horizontal component, but instead of that one, some magnitude of force has created in the vertical direction, that is perpendicular direction, that is MR omega square sine theta. Okay, so this will, that means earlier, if when this unbalanced force was there, your engine was used to vibrate in the horizontal direction like this. Okay, now what has happened? Because of this MR omega square sine theta, your engine will vibrate vertically, up and down, and not to and fro. Because this force is balanced, but this force is unbalanced. So it will, so only vibration you have shifted from along the line of stroke to the perpendicular to the line of stroke. Okay, but what is the solution then? So we always partially balance the engine. Means not completely MR omega square cos theta. We partially means we don't provide M, we provide C into M. Suppose M is 20 kg. We balance suppose only 10 kg, 12 kg, 15 kg. So that C times mass we always balance. So that partial balance should be there. There should be optimization. Okay, means minimum mass should be, or minimum unbalanced force should remain here. That care we take. Okay. So above figure shows reciprocating mechanism with a counter mass M at a radial distance R. Okay. The horizontal component of the centrifugal force due to the balancing mass is MR omega square cos theta in the line of stroke. Okay. This neutralizes the unbalanced reciprocating force. But the rotating mass also has a component MR omega square sine theta, which is perpendicular to the line of stroke. And this remains unbalanced. The unbalanced force is 0 at the end of the stroke because cos theta is minimum over there, 0 over there. When theta is equal to 0 degree and 180 degree, you know, cos 0 is cos theta as sine theta. It is sine theta, no? So sine 0 is 0. Sine 180 is also 0. So when crank is at position 0 degree and 180 degree, this unbalanced force is 0. But it is maximum at the middle. That is when theta is equal to 90 degree. And what is the magnitude? Theta is equal to 90 means sine theta 90 is 1. That means magnitude is MR omega square. The magnitude of the maximum value of the unbalanced force remains the same, is equal to MR omega square. Thus, instead of sliding to and fro on its mounting, the mechanism tends to jump up and down. Okay. To minimize the effect of unbalanced force, a compromise is usually made. That is, 2/3 of reciprocating mass is balanced. Okay, for a value between, or you can take any value between 1/2 to 2/3. Okay, so that we call it as a C. So C is the fraction of the reciprocating mass which is to be balanced. Then, what's the primary force which we are going to balance? It is not MR omega square cos theta, but it is C times MR omega square cos theta. Value of C may be 2/3, 1/2, etc. Okay. So C times MR omega square cos theta, this force we are going to balance. Okay. So what's the unbalance remain then? Primary force unbalanced by the mass. C times we are balancing. So 1 minus C times it is remaining. Okay. Horizontal component we are talking about now, because completely we are not balancing. See here. This force we are not completely balancing now. We are partially balancing. C times we are balancing. So what is remaining in the horizontal direction? 1 minus C times. Okay. That has been shown here. So primary force unbalanced remain is what? 1 minus C into MR omega square cos theta. In addition to this, vertical component of the centrifugal force which remains unbalanced is what? C into MR omega square sine theta. See this horizontal vertical component. Okay. This is MR omega square sine theta, and we are taking C times M, no? So C times MR omega square sine theta is also remaining unbalanced. So now there are two unbalanced forces because we cannot completely balance this partially. So 1 minus C MR omega square cos theta and C MR omega square sine theta, these two forces are remaining as unbalanced forces. Okay. So in fact, in reciprocating engine, unbalanced forces in the direction of the line of stroke are more dangerous than the forces perpendicular to the line of stroke. Okay, that means vertically, this vertical component mr omega square sine theta is less harmful than in the vibrate than this component along the line of stroke. That's why we try to balance this component. Okay, means partially we are finding out the golden mean between these two. So what is the resultant unbalanced force now at any instant? This is the horizontal component of force which is remaining as unbalanced, and this is vertical component of the force which is remaining as unbalanced. Okay, so this and this, as these are perpendicular to each other, we have to take vectorial addition. So R, this is a resultant unbalanced force, is equal to 1 minus C mr omega square cos theta bracket square plus C mr omega square sine theta bracket square. Okay, so this is a resultant force, that is vectorial addition. Okay, so the resultant unbalanced force is minimum when C is equal to 1/2. So we'll try to, every designer will be taking different value. Usually I told you it is falling between 1/2 to 2/3. Okay, the method just discussed here to balance the disturbing effect of a reciprocating mass is just equivalent to as if revolving mass at the crank pin is completely balanced by providing the counter mass at the same radius which is diametrically opposite to the crank. Okay, same we have seen like this at the counter mass. This is nothing but the counter mass. See, you might, if you have seen the engine crank or engine, you might have seen the shape like this. So what does this provide? This is nothing but the counter mass attached at the other end of the crank. Okay, thus if MP is the mass of the crank pin and C is the fraction of the reciprocating mass M to be balanced, the mass at the crank pin may be considered as C into M plus MP, which is to be completely balanced. Okay, that means here what is the total mass? C times M. Okay, what is M? M is that unbalanced mass due to this force, that component. And MP, MP means what? This is the reciprocating total mass that we'll see study in the next lecture. That also is assumed to be placed here. So total mass which is placed here at crank pin is C times M plus MP. And according to this one, we provide the counter mass here. Okay. So now let us see the problem on single cylinder engine. The following data relate to the single cylinder reciprocating engine. Mass of the reciprocating parts is 40 kg. Okay, mass of the means piston, you can say. Reciprocating parts means basically major contributory mass is piston. So mass of the reciprocating parts is 40 kg. Mass of the revolving parts is 30 kg at crank radius. Okay, then speed is 150 rpm, stroke is 350 mm, and radius is 175 mm. Radius means crank radius. Okay, if 60% of the reciprocating parts and all revolving parts are to be balanced, determine the balanced mass required at a crank of radius 320 mm and unbalanced force when the crank has turned 45 degree from the TDC. Okay, now see, as I told you, this is CM plus MP, means here there is a reciprocating mass also we have to assume. Okay, and there is a rotating mass also. Okay, so reciprocating mass, let us see the notation. Reciprocating mass is 40 kg, rotating mass is 30 kg. You know, rotating means we have already studied the rotating unbalance. So what is the rotating unbalance is there? That is rotating mass. And because of this reciprocating parts, which is basically mass of the piston, that is also assume, we have to assume here. Okay, that we'll see in detail in the next lecture. So MRC 40 kg, that means reciprocating mass. MRT is equal to 30 kg, that is rotating mass. Okay, speed is 150 rpm, stroke is 350. Then see how much we want to balance. 60% of the reciprocating parts. That means C is equal to 0.6 of reciprocating parts, 0.6 of MRC. Then balancing radius, that is 320 rpm. MB we have to find out, that is balancing mass. And unbalanced force we have to find out at theta is equal to 45 degrees. Okay, now first you find out the angular velocity omega, 2 pi n upon 60, that is 15.7 radian per second. Okay, now first you find out MC, how much is the mass, means this C times what you can say, this is 0.6 time MRC, no? and then MRT is also there. So how much is the total counter mass you have to provide? Okay, so that counter mass MC is equal to C times rotating MRC, that is reciprocating mass 60 times of this one plus completely rotating mass. Okay, so 0.6 into 40 plus 30. You understood, no? 0.6 of 30, because this is given 60% of the reciprocating parts. So 0.6 into MRC plus MRT will give you counter mass is 54 kg. Okay, now this 54 kg you have to balance. Okay, you cannot balance completely MRC plus MRT. It is given that MRC should be balanced only about 60%. That's why total mass to be balanced is only 54 kg. Now how to balance this rotating mass? You know, MBRB is equal to MCRC. Okay, so MB you have to find out, RB is given, you have to provide the mass at 320 radius. Okay, 320 mm. MC is 54 kg, you have found from this one. And what is RC? RC is here, it is stroke is 350 mm, no? So this radius of the crank is 175 mm, 175. Okay, so MB is 29.53 kg. This much mass, counter mass, we have to provide at the other end of the crank. Okay, now by providing this mass also, engine cannot be completely balanced. So how much is that unbalance remaining? We already found out this equation. You have to take vectorial addition of horizontal component plus vertical component. Okay, so unbalanced force Fu is equal to, we have seen this formula, 1 minus C into MRC R omega square cos theta plus C into MRC R omega square into sin theta bracket square. This bracket square plus this bracket square. Okay, only the thing is that, see, the same formula we have used here. This one. Okay, only here instead of this M, I have called it as a reciprocating mass. Okay, here also reciprocating mass, because that is only going to create the unbalance. So what is MRC? So 1 minus C. 1 minus C is 60% is balanced. So C is 60%. So 1 minus C is 40%. That is 0.4. MRC कितना है? 40 kg. Okay, reciprocating masses. Then R omega square. R is 0.175 meter. Omega is 15.7. Cos 45. Bracket square. Plus, how much is this vertical component unbalance will be there? C times. So C is 0.6. MRC is 40 kg. R is 0.175. Omega is 15.7 and it is sin 45. It is bracket square. So this much unbalanced force is remaining, 880.7 Newton. Okay. So you cannot completely balance the engine, but we partially balancing it, and still after providing this counter mass, 880 Newton unbalanced force will be remaining. Okay. So this finishes your single cylinder engine balancing. Okay. In the next lecture, we are going to study what are the balancing of 2-cylinder, 3-cylinder, 4-cylinder, 5-cylinder, 6-cylinder engine. Okay, and what are their applications, how to balance, etc. Okay, so thank you very much. I will stop here. Hope you have understood the topic.